Hi there. In this video, we are going to be examining the concept of ramps and or inclined planes and pulleys. Now, if you are very familiar with physics a lot, you would know, if you have been solving physics questions, you would know that physics love ramps. Now, what I want to do here is just the mechanics I want to talk about. And what I want to do here is to make you understand the uh, concept, the um, forces on an inclined plane or ramp and pulleys. And you see, I promise you that at the end of this video, you are going to get um, the concept of pulley very well. Because in this video, I'm not only going to tell you what is what, but how it is what. So, why in fact it is what. So, make sure to, sit up and enjoy the video, and also give me a thumbs up as you enjoy the video. And if you have any question about any part that is not clear to you, do well to leave them in the comment section, and I will answer them as soon as possible. As soon as possible. So now we are going to be beginning with now both of these are called the Iran polyclinic plane system and Atwood and pulleys. They are called Atwoods. Now Atwood is just a form of a simple machine that has loads attached to a frictionless pulley via ropes or strings. Do you understand? So that is what is known as Atwoods. Now, um, so basically, Atwoods is a simple machine. So what we want to discuss is how Atwoods work. Now we're going to be examining up to 4 to 5 examples. Is that okay? All right. So the kind of questions you will see on the inclined plane system in WAEC and JAM is the one that asks you to, or that requires you to find the acceleration of a ramp system, of a ramp or an Atwood. So how do we go about finding the acceleration? We're going to be examining that in this video. Acceleration and tension. All right. So look, for example, consider the following ramp. This ramp. We now have a load attached to this string here in this direction, another rope attached here. Let's make this longer. So there's another rope attached here. This will be M2, M1. So mass 1 is attached here and mass 2 is attached here. So, and this is our pulley. So looking at this, you are going to know that you are going to observe that the ramp is basically moving in this direction because and that shows that M2 is greater than M1. I'm going to show you the use of that in a jiffy. Now, before we get into resolving this, you should know the following. Now, we are going to be using the principle of the second Newton's law of motion. That is what will be very useful in the resolution of this. Now, the second Newton's law of motion states that the force applied on a body is directly proportional to the acceleration produced. So, and that can be simplified as that the sum of unbalanced forces creates acceleration. So when forces are balanced, there is no acceleration produced. But when forces are unbalanced, acceleration is produced. So for example, look at this marker in my hand. If I punch it now, it's going to move, it's going to accelerate because there is no force that is countering the movement, the direction of my force. Remember, the third law says that to every action there is an equal but opposite reaction. So now, but there is no equal opposite reaction that this guy is experiencing. You understand? I mean, there's an opposite reaction also because for it to move on my hand, there is friction because my hand is rough, so there is friction that is, acting in the opposite direction. But it's not enough to counter the force or to balance out the force that I'm applying on this body. So that is why this body would definitely accelerate. Do you understand? So the same way, if I punch this phone, which I wouldn't do, of course, it's going to accelerate because there is no equal opposite reaction. All right. So now the reason why we punch the wall and we feel pain is because there is, of course, an opposite reaction from the wall. Is that okay? But that is not what we're getting to. Now, what we're getting to is the fact that forces, unbalanced forces, so we call it F net. the net force. So because we know that a particular force is acting in one direction and there is another force that is acting in opposite direction, call that F2. So the sum of this will give us F net, will give us a particular amount of force which will create acceleration. So this plus this gives us what? ME. Do you understand? F net is equal to ME. That's what we have according to Newton's law, second law of motion. And this is what will be useful in this ramp system. Now, before we begin to resolve that also, there are 2 points to bear in mind, and I'm going to write them in that corner. The first point is the fact that when you want to get the sum of forces acting on the body, we always draw what is known as the free body. In fact, the free body is basically the diagram that shows sum of forces. You understand? That shows the sum of forces. So we said that the sum of forces give what? F net, which is what? ME. Now, you should not be confused by this net, because when we say net means a subtraction. And that is correct because we said unbalanced forces here, meaning that one will be positive, or depending on the amount of force, is that okay? It could be more than 2. So some of them will be positive, the others will be negative. That is why we have F net here. Do you understand? Right. So we have the first thing you should take note of when drawing a free body, or when getting the sum of forces acting on the body, is that any force, so we say forces in direction of motion is going to be positive. But forces not in direction of motion, forces that are not in direction of motion will be negative. So keep that somewhere. So, and if the forces are equal, if they are equal, there will be no acceleration produced. So we said forces in direction of motion are what? Positive, and forces not in direction of motion are negative. All right. So let's using that principle, let's draw the free body of both of these masses and see what the result will be, or what the resulting acceleration will be. Now, keep in mind also that because it is the same pulley, it is one pulley that is attaching them, one pulley. We're going to do an example where there will be more than one pulley in the system. So, but here, because there is only one pulley and one string that is attaching both loads together, acceleration of the system will be the same for both masses. The masses will accelerate equally. Do you understand? Because they are being connected to the same pulley and they are connected by the same string. All right. So for M1 now, let's write for M1. I'd like to clean that. So for M1, we have the free body of M1 will be like this. We say free body is the sum of the forces acting on the body. So M1 is here. Now there is a force that is acting at the center of the, that is maximum at the center of this body, and that is because we are assuming this M1 is a regular body. You know that for regular bodies, the weight, which is the force that is acting, is the weight of the body is always highest at the center of gravity of the body, and which is the center for a regular body. All right. So the center of gravity is where we draw it from. Then we draw it down from the center of gravity. So notice it's not correct to draw it this way. You draw it from the center of gravity. You draw it from the center of gravity. So what is acting downward is also weight. And because this is regarding M1 to be M1G, recall that weight is mass times acceleration due to gravity. And now in this case, if the body were to be on a plane, on a surface, so if M1, if there is a body on the surface as this guy is, now if this body is stationary, because it's stationary, the sum of forces acting on it is different from this one that is being suspended by a string. Because this body here, the forces acting on it are the mass, the weight of the body acting straight downwards, and put that in my emphasis on straight downwards. it doesn't act with respect to the surface, because when we're doing inclines, we will talk about the fact that inclines affect the weight of the body. But of course, the weight of the body, the weight itself acts horizontally, vertically downward, vertically downward. All right, so weight is acts vertically downward here. But for this body, there is nothing suspended, no string attached to it. So the second force, if this body is stationary, the reason why this body is not pushing into the ground, or is not pushing into this, or maybe more like imagine it, it's not pulling into the weight is not pulling it to enter into the ground. Say this was the ground, is because just like I am standing on the ground, the reason I'm not entering into the ground, even though my weight is pulling me down, is that there is another force that counterbalances the weight, and that is the force that is acting relative to that is acting between the surface of this ground and the bottom of the body. So there is a force for me now. There is a force acting underneath the sole of my feet and the ground, between the sole of my feet and the ground. So that force we draw from the ground here is what is called the normal reaction, or you must see R. It's denoted by N or R depending on the convention that your textbook uses. All right, so you see, because of these forces balances each other out. So one is acting, so there is no direction of motion here, so we can make any one positive. We'll make R positive and make weight negative. Given that R is equal to weight, therefore we'll get 0, and that is why there is no A. Do you understand? There is no acceleration, so this body is stationary. But that is different in this case, because here there is no normal reaction acting here. And why is there no normal reaction acting here? That is because this body is not sitting on the surface. This body is being hung, is being suspended by a string. So because the string is the one suspending it, there is no normal reaction. Instead, what we have on a string, the force that is always acting on the string is what? Tension. So tension is going to be acting even on the string also. But the direction, now let me not draw the direction, but the direction is what matters now. Because we said forces that act in direction of motion will be positive, and forces that act not in opposite direction will be negative. So before we examine the forces, first understand the direction rather. Before we examine the directions, first understand the fact that tension is always the force acting on the string. And that is because it's the force that the string will feel. All right. Now, what is the direction? So we already know that something is acting downward here, which is the weight of the body. Okay, we've said that here. And what will be acting upward here? That what? The tension in the string. Tension in the string. Now, I've talked about direction already then. First, notice that I did not say T1 and T2. And the reason why it's not T1 and T2 is because the rope is the same. So if the rope is the same, if the rope were to be different, so there's one system we're going to be examining probably before the end of this video, that you will see that, okay, so if there is a mass here, and a mass here. Now this rope is different from this rope, so because of that we experience different tension. So T1 and T2 will apply here. But T1 and T2 do not apply here because the rope is the same. So tension is equal across the rope. So that's why T is what we are using here. Now, we said that these are the two forces acting here. There's no force in this direction and there's no force in that direction. Alright, so now we said also that tension is acting upward here because weight is pushing down. And of course, if you had cut, the best way to view it is that if you had cut this rope here, around here, where will this rope move? To move upwards. Do you understand? Because the rope is down, the weight is pulling it down. So tension is felt in the opposite direction. As well here, tension is felt upwards because this weight is also pulling the rope down. If this rope were to be cut here also, you see the rope move upwards to show that there's a force pulling it in that direction. But these forces are unbalanced. That is why this system will move. Do you understand? Now, so let's do the sum of forces now. The sum of forces is going to be for M1. Now, where's the direction of motion? Seeing this ramp here, you are going to notice, of course, when you are given the weight, the masses of the body, you will know which one is greater. So, for example, I told you this way to be 20 kg and this way 30. You know that this system is moving in this direction because this weight is heavier. This mass or weight is heavier, yes. So, or weight is larger or mass is larger. So, it means that this system is moving in this direction. So, let's see. So, tension here on this string, we said is moving upwards, right? So, tension will be positive because it's moving in direction of motion. Is that clear? Then weight. Weight in this case is moving downward, which is opposite to the direction of motion. On this side, motion is upward. So weight is moving downward, so weight will be negative. So if it was plus minus W, because they are both for forces, but one is positive, the other is negative. So sum of forces, therefore, will be equal to T minus W. And summation of forces will give us MA, right? So let's put that on the other end. So what we'll have here, therefore, will be T minus W will be equal to MA. But MA here will give respect to M1. So we'll call it M1A. M sub 1A. Alright. Now, what is the weight of the body? M1G, we said. So tension, therefore, will be equal to tension minus M1G will be equal to M1A. So, and this is equation 1. Alright, let's call this equation 1. Now, for body 2, for M2, we're also going to draw the free body of that to analyze the sum of forces that are acting on it. So for M2, right? For M2, the free body will be something like this. There will be a weight, a force acting downward and tension acting upward also. So the same thing, but no, keep in mind that tension is the same here. Tension is the same here. So weight in this case will be M2G. Weight in this case will be what? M2G. So it therefore means that the sum of forces on this guy will be equal to what? Tension is now here. Tension is opposite the direction of motion because motion is in this side it will be downward since the body is moving like this. So in this on this side, motion is downward, tension is opposite. So tension will be minus T plus what is the weight of this body? M2G, M2G, and that will lead to this unbalance MA, right? So we can rewrite this as M2G minus tension is equal to M2A. Does that make sense for that guy? All right, this will be equation 2. Now, from equation 1, we can form equation 3. All right, so that C can be equal to here M1A plus M1G. All right, and this will be equation 3. So we can now substitute to know if tension is not given, to know the value of our acceleration since tension is not given. We can substitute equation 3 for T. So this guy M1A plus M1G will be substituted for T. So we therefore have M2G minus, since tension is M1A plus M1G. So we put it in bracket because it's an expression, it's not just one value, value. So we have to put it in brackets because this minus might have an effect on the expression. So we have M1A plus M1G is equal to M2A. All right. So this we have M2G, by the time we open the bracket, M2G minus M1A plus M1G is equal to M2A. Now, given this, we can now collect like terms, MA and NA as collect together. So we have M1, let's write this first, M2A, when M1A goes there, or for those that might be confused, let's just write what we have first. We have M2G plus M1G will now be equal to M2A. Here comes a plus M1A. Alright, so since it's acceleration we're looking for, acceleration is common there. So we have G is also common here. We can say G into bracket M2 plus M1 is equal to A into bracket M2 plus M1. So from here, oh, there is a mistake. There is a mistake. I said that minus will impact this. M minus times this will be negative here. Negative. Negative. So here, it will also be negative. It will be negative when this guy goes there. So this place also is negative. Alright. So you have to be careful as you do it. So it means that if we divide with to make a subject, we divide size by m2 plus m1 over m2 plus m1. So that A therefore of the acceleration of the system is equal to G into bracket m2 minus m1 all over m2 plus m1. Right? And that is the acceleration of this system. So for whatever values of masses you are given, just plug them into this equation and you get your acceleration. So for example, if you are given that this guy is 20 kg and this guy was 25 kg, we still know that this guy will move in this direction. So our acceleration for that system will be kgs. Let's put their units. So for something a question like that, it means that A will be equal to G. G is 9.8 into bracket m2. Let's make this 30 so that let's just make it 30. I like to work with numbers with zeros. All right, so m2 as 30 minus m1 20 into bracket m2 30 plus 20. All right, the numbers with zero will make the work simpler. That's what I'm saying. So 9.8 times 10 into bracket 50. So we have 98 over 50, and that's approximately 2, because that will be 1.96. All right. So the answer will be 1.96 meter per second squared. So acceleration is 1.96 meters per second squared. That's approximately 2. So that's if you are given the values of the acceleration. Now, let's consider the second ramp system. Let me clean the board. Okay, so seeing that now the second type of system might be given is an inclined plane or a ramp. Now, so we are given a ramp here like this. Let me make it well inclined. That is, I'm reducing the angle of inclination so that you will. So there is a pulley here. So let's say that's the pivot of the pulley. So the pulley is attached. Attached to the pulley are two masses, m2 and m1. Okay. So now you have to determine the acceleration of the system, and here they are inclined at an angle of theta. So you are told to determine acceleration of this system. Now there are two things you must take first. You should draw the free bodies the same way we've been doing. Draw the free bodies of both masses of this square. Okay. So draw the free body of both masses. Draw the free body of both masses. So for M1, so the free body of M1 will be, now looking at this, there is a force acting in this direction, and because there is a surface here, the weight of this body, since this body is sitting on the surface, the weight of this body will act in what direction? Remember, straight downwards. That will be weight, which is equal to, in this case, M1G. The weight of the body is always vertically downwards, and draw it from the center of gravity, I've told you. Then there is a force that is in the opposite direction, which is from, and that's normal reaction, right? Normal reaction, weight acts from the center of gravity vertically downwards. Normal reaction acts between the surface, which I've said before. Normal reaction will act between the surface, so you draw it straight upwards relative to the surface. Now you must draw it to be directly perpendicular to the surface. To be perpendicular to the surface. It's usually a rule of thumb is to draw it in a way that it will coincide somehow with the point where you drew your center of gravity from. So normal reaction between the surface and the base of this, mass is going to be given as R or N. Let's use R. I want to use the convention R. Okay, so what that means is that relative to this surface, the angle, there's an angle here, 90 degrees. This is at right angle here. Do you understand? All right. Now, if normal reaction is acting upward, then this body should be pushed up. But there is a counterbalancing force that makes the body to stay on the ramp. So which means that R has no effect on here. And that force is going to be mg. Now wait, that will be m1g cos theta. Now wait, I'm going to show you how this came about. Is that okay? Where it comes from. All right. But for now, understand that it is m1g cos theta. And I've told you I'm going to tell you why and how. Then there is also one force here. Because this body, if there was no rope here, this thing will naturally slide down. But there is a rope attached here. So it means there is a force that is also pulling it in this direction. We can think of it as if this were a friction, a rough surface pulley, then that will be frictional force, right? And that will act in this direction. That will be m1g sine theta. I'm going to tell you how also. All right. So how did we get that? Still on here. So what will be acting now? If in this case the system was to move in this direction, let's say the system was to move in this direction, it means that m2 is greater than m1 again. Okay, that was what we did the other time. Okay, so it's still the same thing. M2 is going to, so the system will move in this direction with the same acceleration because the string is the same and it is one pulley. And because it's one pulley, tension will also go what? The same. Well, let's examine the directions of tension. In this place, this guy is acting downward here, right? Since this guy is pulling downward here, that is a frictional force, or just basically the position of this pulley. Because of the position of this pulley, there is a force that is of this ramp. There is a force that is pulling this guy here. So because that force is pulling in this direction, tension will therefore act in the opposite direction. I've told you, when you say suspended body with a ramp, know that force tension is always acting in opposite direction to the weight of that suspended body. So also, it means that what will be acting down with the weight, which is in this case m2g, is going to be countered by the tension that will act in the opposite direction. Okay, so we have talked about the direction. Now let me now go back to how we came about this. Let me go back to how we came about this. First, how did we know that theta will be here? This theta is this theta here. How? Because the angle between this guy and this guy is theta. And let me break that down for you. Now, how did we get that? It's very simple. It's very simple. So what we have here is basically theta here, and we have relative to surface another angle that is perpendicular. So these are 90 degrees, 90 degrees, 90 degrees, 90 degrees. Does that make sense? So I just drew this point here, this point here. So if this angle is theta, and we have another force, not force. Yeah, it's a force, the weight. So weight is downwards and it's making 90 degrees here. If it's theta and this 90 degrees, it means to get the angle here. Remember, this theta here is the angle here. If you look at it well, what I just drew here. So if this guy is 90 here, let's call this alpha. Alpha will therefore be, if sum of angle in a triangle is 180, so it means that 90, it means that if we already have one as 90, the remaining two we add up to 90. Does that make sense? So this plus this alpha plus theta should give us 90. I already know what theta is. So what is alpha? Alpha will be 90 minus theta. Is that okay? Alpha will be 90 minus theta. So if alpha is 90 minus theta, and remember also that I said with respect to what I just drew here, this thing also what? 90 granite, right? This place is 90 granite, and this place is alpha. So if this place is alpha, and alpha is just 90 minus theta. It therefore means that the remaining here, that this guy needs to make 90 degrees also what? Theta. Does that make sense to you? This place is 90 minus theta. So, and this place is theta. And both of them, yes. So alpha is 90 minus theta. And the other side plus theta. Do you understand? Everything must be what? 90. Is that okay? So if we subtract 90 from both sides, I hope that makes sense to you. That is alpha plus theta is equal to 90. And we know that on this side, alpha is what? 90 minus theta plus theta. So, and this one should give us, everything should give us 90 degrees, right? Since everything should give us 90 degrees, it means that theta, if everything gives us 90 degrees, by the time we subtract 90 from both sides, theta will be equal to theta. Do you understand now? Because if we add up this alpha and theta here, or this alpha and this place, we will get 90. So we are proving that, I'm proving that it is also theta. So, and this is it, theta is equal to theta. So this place is this place. I hope that is clear to you. There are many other ways to prove it, but so that I will not waste the time, waste our time. Let's just go to, because usually in exams you will not be asked to prove anything, but I'm just trying to, because I promise you that I'll show you where it's coming from, or what is what and why it is what. All right. So in that case, that's why we got this theta here. Now, how do we now get m1g sine theta and m1g cos theta? Now, if you see my video, I'm going to try and link it here on the description of this video. If you have seen my video on equilibrium of forces of vectors and all of that, resolution of vectors, you would have seen that I said on resolution of forces, we talked about the fact that we talked about this guy's equilibrants, and how to draw them. So remember that in triangular law of vectors said that the two sides of the triangle are represented the magnitude and direction. So let's say this guy was moving in this direction, this guy was moving in this direction. If they are moving in the same direction, the resultant is the diagonal in the opposite direction to which both of them are moving. If they are moving in opposite direction, then you can draw the resultant force arbitrarily. I hope that makes sense to you. And we said that the equilibrant is a force that is equal in magnitude to this guy, to this resultant, but is opposite in direction. Right? We're not getting into that now. Let me just show you what I'm trying to talk about here. Now, if we took this system here, let's use only this system here to analyze this system here, this triangle formed here. Now, I'm going to close this triangle here so that this place will be 90 degrees. So what we have is what? Now, and the reason why I'm using this guy is because this guy shows me mg. Because these two forces, the force acting here and the force acting here, they have one resultant, only one resultant. That is if we drew it this way. The resultant is what? mg. Do you understand? Either way you want to draw it. The resultant of these two forces here, one is acting here, one is acting downwards here in this direction. The resultant of what? Weight. When you sum them up, you get weight. They cannot be more than the weight of the body. All right. So since the resultant is weight of the body, then let's call this place x. So if this is x, it means that what we mean is this place will be x. Horizontal component will be x. So this will be x, and this is mg, weight of the body, for m1 now, but I'm not putting mg. I just want to show you how we got that. Then this side therefore will be y, which is this guy. Do you understand? So now how did we get y? You know that our angle, okay, since we brought out this triangle, our angle will be here, theta. But we have brought out this triangle here, it will be like this. So our weight is mg, this place is x, this place is y, and our angle will be, now in this case, our angle will be here. Our angle will be here, theta. Okay, but that's not what we're getting into now. So, but I hope you understand what this is. I brought out this triangle, and the reason I use this one is because this one already contains the resultant, which is weight. So this weight, and then there is one that is acting, and I have to make them perpendicular, right angle. So this weight, this thing that is perpendicular to this will be equal, so that will be x, and this place is y, right? So and the angle is here. So to now find x will be equal to the horizontal component will be equal to what are we going to use? We know SOHCAHTOA, right? So this is already the hypotenuse, and what we have here is the opposite. So x is opposite, so we have sine of theta. So sine of our angle theta will be equal to opposite, which is x over hypotenuse, which is mg. So x therefore will be, if you cross multiply, you get mg sine theta. So that is the x component. That's how we got this. And also for this guy will be adjacent. If this is a right angle, of course, this will be adjacent. Why? So cos of theta will be adjacent, which is y over hypotenuse, which is yes, hypotenuse, which is mg. So y therefore will be equal to mg cos theta. So this is where these two things are coming from. Now, another way to view it is this, and this is also a trick. This is also a trick. What you will do is that once you see an angle here, you want to get the force that balances out normal reaction. That normal reaction is not being experienced here. The force that balances out is m1 cos theta. And how did you get that? Just come in and resolve this to this straight line here. Resolve this weight in this direction. If you resolve in this direction, you will see that you are closing the angle. So whenever you close an angle, you use cos to close. And I've talked about this in our other videos. I think in projectile motion, right? And even in vectors, all right? So sine, when you open an angle, you use sine. Do you understand? You use sine to open the angle and use cos to close the angle. How do we know we're opening an angle here? By the time we resolve this weight to the horizontal component relative to this plane, we'll see that this will be opening this angle, that is 1g sine theta. I hope I've been able to do justice to that. All right, so that you don't need to cram, basically. You don't need to cram. Just understand what is what and why it is what. All right, so I said that we want to obtain the acceleration of the system. So let's draw the free body of M1. So we know that M1 is here. So the sum of forces on this body will be M will be here. Now, the one acting upward and downward, normal reaction and this balance each other out. So since they balance each other out, we don't need it. You understand? If you like, you may just want to draw it and M1g cos theta. So since R equal to M1g cos theta, that will be sum will be 0. The acting opposite direction R minus M1g cos theta equal to 0. Right. But there is another force, one acting in this direction, the other acting in this direction. The one in this direction is M1g sine theta. And the one acting in this direction is tension. And they don't balance each other out. They are unbalanced forces. And recall, Newton's second law of motion. Unbalanced forces causes acceleration or bring about acceleration. So we'll say that tension. Now, where is the direction of motion? Direction of motion is here, right? So which one will be positive? The one in direction of motion will be positive. So tension is positive plus this guy, M1g is opposite direction. That is minus M1g sine theta. Recall that this is M sub 1. So this will lead to what? A particular acceleration of M1. So what we have is T minus M1g sine theta is equal to M sub 1a. I hope it's still capturing. So what we now have here will be M1g sine theta. So what we now have here. So that's that. Let's call this equation 1. We can make it equation 2 from here for tension. Tension, if tension is not given the question, so M1a plus when this guy goes there, plus M1g sine theta is equal to M1a plus M1g sine theta. So let's call this equation 2. And let's now resolve for the sum of forces on M2. M2, because it's not on any surface, we know that the free body will look like this. What is acting downward? M2g. And what is acting upward is tension. Tension always acts upward for a body that is suspended. Is that okay? I'm always acting opposite direction of weight, which will be upward in this case. So we have sum of forces, summation F equal to tension is opposite direction of that will be minus T. Weight is in the direction of motion on this side, since the body is moving like this, because M2 is greater. Don't forget that. So we have plus M2G will give us M2A, acceleration on MA. So we now have M2G to arrange correctly minus T is equal to M2A. All right, let's now substitute this into equation 1, into equation 3. Let's call this equation 3. So let's substitute for T if tension is not given, because tension might not be given, but usually is not given in the question. So especially in questions that are required to find the acceleration of the system, now. So substitute this guy into it, and we'll have that M2G minus Now, because it's an expression, also put it in brackets, m1a plus m1g sine theta. m1a plus m1g sine theta will be equal to m2a. So we have m2g minus m1a. Don't make the same mistake as I made the other time. Minus times plus here, minus m1g sine theta will be equal to m2a. All right, from here, we can collect like terms so that we have m2g minus m1g sine theta is equal to m2a plus m1a. So a is common, g is common here also. So we can say g into brackets m2 minus m1 sine theta is equal to a into bracket m2 plus m1. We are particular about making a subject formula. So we can bring this here. Acceleration will now be equal to a into bracket, so let's just write what we have there. A into bracket m1 m2 plus m1 equal to g into bracket m2 minus m1 sine theta. Okay, so we divide both sides by m2 plus m1. Of course, you have a will be equal to g into bracket m2 minus m1 sine theta all over m2 plus m1. All right. So that will be it for this system. Now, what if we were given another type of ramp? I want us to resolve every possible type of ramp that we can see, or Atwood that we can see in exams. So let's resolve the second one. Okay, this is number 2. Let's resolve number 3. Number 3. Let me clean the board. All right, so we are going to be, and I look different here because I quickly took the opportunity I had to cut my hair. All right, so let's continue what we're talking about. So how do we how do we, do this sum of forces or determine the acceleration of the system? So let's still use the fact that m2 is greater than m1. So in this case, if m2 is greater than m1, it means that the system will go like this. Now I want you to know that if m1 was greater than m2, acceleration of this system will be 0. Because this system will not move at all. What will just happen here is that this thing is going to suspend this guy, this way to suspend this guy, if m1 was greater than m2. But for this system to accelerate at all, m2 has to be greater than m1. m2 has to be greater than m1. And if m2 is greater than m1, this is what we're going to have. First, we draw the free body of m1. Now, m1, so for m1 now, the sum of forces acting on m1. We know that m1 is on the surface of this thing, is sitting right on this thing. So we have that the weight of m1 will act vertically downwards. So weight will act vertically downwards. So W equals m1g of m1. Then between the surface of this body and the base of m1, something is acting upward, which is what? Normal reaction. And since both of them balance each other out, it's almost useless here. Alright, but it's good to still depict the forces acting on it. Now, how about here? What force will be acting? So since the system is moving in this direction, it means that there is a force acting on this rope because of this weight. So weight has been cancelled out here by normal reaction. Remember, weight has been cancelled out by normal reaction. And because weight is cancelled out by normal reaction, it therefore means that there are two conditions. Condition one is that if this body, if the surface is rough, condition one is the rough surface condition. So in the rough surface condition, what would happen is that as this body is being pulled in this direction, tension will be acting in this direction also. So tension will move in the direction of motion, but something else will be acting in this direction. Because this surface is rough, to experience a frictional force, which is equal to mu r. If you remember the formula for frictional force. So F equal to mu r. So mu stands for the coefficient of, now at the stationary point to be coefficient of static friction, so we'll call it mu s, and mu k for coefficient of kinetic friction. Then mu s, that is coefficient of static friction. All right. So for condition 1, the force that will be acting opposite will be mu r, and the force that will be acting in this direction will be tension. So tension, because it's the same string, so tension, so summation of forces here on this guy is going to be tension, which is on in motion, direction of motion, so it will be positive, and F, which is frictional force, or F sub r, which is in opposite direction of motion. So what we have here will be T minus, this will be mu r equals M1A. Does that make sense? So that we have T here with minus mu is mu. Is that okay? And it doesn't have units. R is mg, that is M1G in this case, is equal to M1A. All right. Okay, we might, so this condition 1. So if that is the case, then M2, this condition 1. So for M2 now, for M2 here, the sum of forces, we've said what we act upward, since weight of this body we act downward, weight reacts downward. So for body 2, mass 2, we have from center of gravity we have M2G, and upward we have tension in the string. So direction of movement of the system is downward. So weight is positive, then but tension is negative, is equal to M2A, the acceleration of the system. All right. So we now have W, which is M2G in this case, minus T equal to M2A. So if this is equation 1, this will be equation 2. All right. Now we can now make equation 3 from here, so that T will be equal to M1A plus mu M1G. All right, this is equation 3. So we now substitute equation 3 into 2 for T. So substitute. You know that, just plug this whole value, this entire thing, into this equation in place of T. So what you have will be M2G minus all of this, because it's an expression, as we said before, the first one of inclined plane, we said because an expression is going to be this, something like this, then plus mu M1G. So it's equal to M2A. So what you now have here will be M2G, you open the bracket, minus M1A minus mu M1G is equal to M2A. So from here, we can now collect like terms, so that we have M2G minus mu M1G is equal to M2A plus M1A. So what is common? A is common here, and G is also common here. So we have G into bracket M2 minus mu M1 is equal to A into bracket M2 plus M1. So A, therefore, will be equal to, divide both sides like this, so that we now have G into bracket M2 minus mu M1 all over M2 plus M1. And that is the value of the acceleration for the system under condition 1. Under condition 1. But for condition 2, is even central. Let's just leave that. Condition 2. If condition 1 is rough surface, so it means that condition 2 will be what? Smooth. If the plane was a smooth plane, or smooth surface. So if the surface was smooth, now condition 2 will be that if the body is smooth, there is no frictional force. So if there's no frictional force, tension is already acting in direction of motion. So summation of forces is going to be equal to, tension is in direction of force, so it will be positive, plus no force is in direction of, is in opposite direction, or minus no force is in opposite direction. So we have this. Therefore, we have T will be equal to M1A. M1A. Now, so that's equation 1 for this case. All right. I hope that, so we have There's no force that is opposite. Do you understand now? No force is moving in opposite direction. That's correct. So no force is moving in opposite direction here. But tension is moving in the positive direction. So it's positive, no frictional force because it's a smooth plane. So the body will slide without any friction injuries. Or with very negligible friction, negligible amount of friction. So that's why we just say -0. All right, so we have T equal to M1A now. So what do we do next? We'll now draw for M2. So this is for M1. So this is M1. Now for M2, we'll have the same thing for M2. Nothing changes for M2. So we said weight minus T is equal to M2A. So that M2G minus T is equal to M2A. All right. And T is already M1A, right? So since T is already M1A, we'll now have substitute this equation 2 here. So sub equation 2 into 1 for T. So we have M2G minus T is equal to M2A. These are equations. So anywhere we find T, we substitute M1, M1A. So M2G minus M1A is equal to M2A. So what we now have here is we want to make A subject. So let's correct like terms. So M2G will be equal to M2A plus M1A. So what we now have is M2G will be equal to A into bracket M2 plus M1. So that A is equal to M2G. Divide both sides like this guy. M2G over M2 plus M1. Okay, if I now that I look at it, so far, all of this thing we've been doing from that first one that we did the other time, from inclined plane and all that, up to this one. M2 plus M1 has been our denominator. Even here. You see it? Right. So that's that on this one. Then let's go to the next, which is motion on. We resolved this. So we resolved inclined plane just now. This. How about we have a three? Okay, no. How about we have double inclines? Double inclines. Let's resolve one on double incline. Let me pause that and clear the board. Okay, so what if we have case 4, a double inclined plane? So we have something like this. They could be inclined at the same angle, and they could be inclined at different. Let's do one for different angles. Is that okay? There's just so many things you can do. We can do the one for the same angle and one for different angles. Let's say they were different angles. Or no, let's start with one for same angle. Same angle. So if this theta, this theta. Then no. You will do one for same angle and tell me the answer in the comment section. In the comment section. Do one for same angle and tell me the answer in the comment section. We're going to do one for different angles. So this one is inclined at alpha. Is that okay? So we have so let's call this M1 and call this M2. Both of them are attached to a pulley here. All right. So if you had a system like this, and you are told to find acceleration of the system, find E of the system. It's very simple. So I won't be having to prove anything again now because I've told you how to prove this on incline, the second one that we did. So here there is weight is acting directly downward. So we have mg, that is m1g. So let's assume that m2 is still greater than m1. In any direction, we can choose any direction. So in this case, this guy is still moving in this direction. Do you understand? Whether it moves here or here doesn't affect for this one because it's double inclined. So m1g here, and then there is perpendicular to the surface, there is normal reaction acting there, and the force that balances it out is m1g cos theta. I know we've said that before. Cos theta. Let's bring it up because of the space. m1g cos theta. So And recall that because of what we have shown that before too, that if this were a right angle, this angle here too would be theta. Do you understand? Right, the same way, here we'll say that right perpendicular to surface is r, then then from the center of gravity, what is acting straight down is m2g, that's the weight of this body. Then the one that balances that guy out is m2g cos theta. All right. Then there's a this thing, a force acting downwards there. That will be frictional force if this surface was rough. And even when it's smooth, the weight can be resolved in this direction also. Do you understand? So we have m1g sine theta, m1g sine theta, and here also we have m2g sine theta. And I've told you that before. Down the inclined plane sine theta. Then on this side, or this side, we have cos theta. I think this is what we have here, and that is all we wanted. So we'll now begin to, you know, um, find the sum of forces. So for M1 now, for M1, we already know that this one balance each other out. So the forces are acting here. Tension is also acting here. So if this guy is moving in this direction, tension will be in which direction? Mg sin theta is pulling here. Tension will be in that direction. Mg sin theta is pulling here. Tension will be in this direction. All right. So tension is the same because it's the same string. I keep repeating that. It's the same inextensible string. Yeah, keep in mind that the string is also, that's also one of the conditions for this to be true. Inextensible. The string has to be inextensible. I'm going to link the video to elasticity, right? You know what is extensible string, you know. So F equal to F for M1 rather. How do we, so we say the sum of forces on M1. Yes, summation of forces on M1. We have that this guy is acting there and direction of motion is there. So tension is positive, then mg sine theta is negative. So we have m1g sine theta. So here we have t minus m1g sine theta is equal to m1a. So t can therefore be equal to this equation 1. So t can be equal to m1a plus m1g sine theta. All right, this should be equation 2. Then we can now draw for m2. For m2, we have summation of all the forces here will be equal to, for m2, tension is in opposite direction, so tension minus t, but m2g sine theta is in direction of motion. Okay, so that we have summation F will be equal to m2g sine theta minus t. Okay, so this is equation 3. We can now substitute. Sub m1a plus m1g sine theta for t in 3. Do you understand? So in equation 3, we'll substitute this guy, this whole thing, for t. So what do we have? We have that. Recall that equation 3 is, okay, you notice summation for that is MA, right? That M2A is equal to M2G sine theta minus t. This was our equation 3. So we can now say, since we are substituting for t, M2A will be equal to M2G sine of theta minus this entire thing. Always remember to put the bracket. M1A plus M2G sine theta. Is that okay? And here we have M2A is equal to M2G sine theta minus M1A minus M2G sine theta. So we can now collect like terms. So this guy can come here. We have M2A plus M1A is equal to M2G sine theta minus M2G sine theta. Oh, I'm sorry. M1 It's M1G, M1G, M1G. So because it was going to give us 0. All right, so we have A is common, right? A into bracket M2 plus M1. Yet again, this guy will be a denominator. Is equal to M2G sine theta minus M1G sine theta. So divide both sides by M2 plus M1. M2 plus M1. What do we have? A is equal to what? M2G sine theta minus M1G sine theta all over. And you can, decide to put G, like G into bracket M2 sine theta minus, you understand what I'm saying, right? The way we've been doing that one too. All right, so this is the acceleration of this system. So for whatever mass given and the angle, you can do this. Oh, I'm sorry. We were to use different angles. So either ways, this would be mg sine phi. So what will change is just this. Do you understand? That's what will change. So M2 is always carrying sine phi. So M2 here should be sine phi. Okay. So in fact, I've already done the one I said you do in the listen. Good afternoon, sir. Yes, sir. Yes, sir. So here we have acceleration will be equal to M2G now sine phi. Do you get it now? Minus M1G sine theta. Alright. Over M2 plus M1. So and that is it for this. Okay, let's do one more, which is the one that consists of three systems. Three systems, and this is not with an incline, but it's also an Atwood. So what if we had something like this, number 5? What if we had a system like this? So I have this. I have our pulleys here. Let's name it M1, M1, M2, and M3. Alright. Either way you want to do it, it's simple. It's very simple. What you want to do is still the same free body, the free body of this now. So for M1, here's what we have. M1 comprises of two major forces. M1 has two major forces acting on it, which are the one acting upward, the tension will act upward because the weight will act downward. Do you understand? So we have this. It's good to draw the free body. Do you understand? Even though at the first instance you think later on you know it's a waste of time if you really understand. Okay, so it means that the summation of forces on M1 will be equal to tension, which is now, okay, which one is greater here? If M3 is greater than M2 and if M3 is greater than M2 plus M1, so this is a condition, please. Let's add this condition. If M3 is greater than M1, M2 and M3 and M1, M2 plus M1, the system will go in this direction. And if M1 was greater than M3 and M2, M1 greater than M3 and M2, the system will go in this direction, and that is anticlockwise. And if M2 was greater than both of them, then the system will not move at all. The system will be in equilibrium. Right, so maybe not even equilibrium, but at least to normal. That's the thing, to normal. So we have summation F because M1, so the system is moving like that. Tension is moving in direction of motion, so that's T. You understand now? This is the case where M3 now is greater than M2 plus M1. All right. So the entire system is going that direction, so tension is positive minus weight is negative. That's M1G. So we have T minus M1G is equal to M1A, equation 1. Equation 1. Yeah. So let's draw for M2. Now for M2, what are the forces acting on it? Now, recall that there are two strings here. There are two different strings here. Because one string is attached to the right arm, the other string is attached to the one. This one. This one. The first string is attached to the right arm, the second string is attached to the left arm. So the tension here will be different from the tension here. So we'll call this T2, while we'll call this T1. Do you understand? Tension on this string we'll call T2, tension on this one we'll call T1. They will be different. So here we are referring to T1, T1. All right. So for M2, T1 will still be acting on it, but in what direction? So here, T2 here, T2 here. All right. But let's decipher the directions. Now with this guy, with M2, since the entire system is moving here, something will be moving in opposite direction there. First, tension here will be felt in what direction? Since the system is moving that way, tension here will be felt in the opposite direction. Do we understand that? The system is moving here, tension will be felt in the opposite direction. Recall also that weight is acting downwards and normal reaction balance each other. So both of those will not have any impact. Then, now, this system is going like this. Tension is also going in direction of motion. On this side, T2 is in direction of motion. T1 here. So T1 is acting on this body. So here, in this direction, for M2, in this direction, we know that T1 is acting in that direction. Because this body is pulling, is pulled towards the direction. Therefore, T2 is going to act in direction of motion, move in direction of motion, because I remember I intentionally cleaned that because I thought we're going to write a lot here. So just remember, the one in direction of motion positive, the one in opposite direction negative. So this guy is in direction of motion, so T2 will be positive. So, and I guess that's it. That's it. Another condition is if this surface is rough, okay, maybe we'll add that. So we're going to do two conditions for this too. So let's say condition 1, rough surface. Condition 1 now. Condition 1, rough. So if this surface were to be a rough surface, this surface here, then it means that since motion is like this, friction will act in opposite direction to motion. That is F sub R, which is what? Mu R. So it means that the sum of forces here that is negating motion are T1. You have to know. This one. This one. So the sum of forces negating motion here are F sub R and T. The sum of forces in line of motion is only T2. T2. So for M1, M2, what we'll have is this. Let's bring that up here. So for M2, what we have is this. T1 is negative. This guy is also negative. So that will be minus T minus F sub R plus T2 is equal to M2A. I hope that is clear. Keep in mind that acceleration will still be the same because all of them are attached together. Acceleration will still be the same. Okay, or you can just say T plus this. Like, there are two ways to do this. You can say, so here we have T2 minus T, minus T1, and minus F sub R, right? Or you can just say that it is T1, T2 is positive plus T plus T minus T plus F sub R. So either way, you still get this. Okay, so that's correct, I think. That's correct. Remember, this is a rough condition, so friction will oppose motion in that direction too, because the system is moving in this direction. All right, then tension T1 will also oppose motion, right? When it's pulled here, tension will be felt in that direction. Do you understand? Tension will be felt in that direction. All right, because if we cut this rope here, this thing will go that direction. Okay, so we have that this is equal to M2 sub A, M2A, M sub 2A. So So from here, we can make equation 3 first. Let's quickly make equation 3 here. So T1 it will be equal to M1A plus M1G. This will be equation 2. So this was our equation as equation 2. This will be equation 3. Equation 3. All right. So what do we do from here? How about for M3 ahead? Let's consider for M3. For M3, what will be the case? You know that the free body of that one is very simple. This guy is going up, weight is acting upward. Upward is negative to the direction of motion. Downward, which is weight, is positive to direction of motion, M3A. A because they are all moving together. Understand? Yes, sir. So we have weight, which is now M3G minus T is equal to M3A. But T here is T2. Okay, don't forget that, please. T here is T2. Okay, since we have T1 and T2 here, we can just substitute. Let's make, this will be equation 4. So let's make equation 5 here. Equation 5 will be, this guy will go there, this guy will come here. So we have T2 is now positive, is equal to M3G minus M3A. Does that make sense? So, so we'll now substitute. So this is equation 5. So we'll now substitute sub M3G minus M3A for T2 and M1A plus M1G for T1. Keeping in mind that in your question you might not be given tension, so you always solve in a way that you will give only masses. Mass is the only thing you be given. Mass is the only thing you be given, so you have to find the acceleration of the system by yourself. So we are substituting this for T2. So recall in equation 3. In equation 3. So let's bring it here. So recall that T2 minus T1 minus F sub r is equal to M2A. This is equation 3. All right, with this, we know that T2 is now M3G minus M3A. Then minus T1, which is M1A plus M1G. Is that okay? So then minus F sub r. And F sub r is mu r equals to mg in this case because there is no inclination, no angle of inclination. So r equals to mg. So here is mu mg that we have. But this case, F sub r here, let's not make the mistake. F sub r here is for m2. So that will be m2g. I hope that is clear. As in this is what I mean. Mu r. Is that okay? Given that F equal to F sub r equal to mu r, and which is equal to m, since r is equal to m2g, that will be mu m2g. So it means that what we now have will be equal to, everything here will be equal to m2a. So we now have that m3g minus m3a minus m1a minus opens the bracket, minus 1 opens the bracket. We have m1g minus mu m2g. Mu m2g. So that this will now be equal to m2a. Alright. So what we have here is, let's call it like terms. The guys are happy. Let them come together. So we'll have that m2a. This guy goes there, will become plus, let's guy go first. Plus m1a plus m3a will be equal to, what we'll have here, these ones are gone. What we'll have here will be m3g minus m1g minus mu m2g. And in this case, you'll be given the coefficient of friction, don't worry. In a case where friction is to be considered. So A is common between m2, m1, and plus m3. Okay. Then in this case, G is common between m3 and minus m1 and minus mu m2. Alright, so our acceleration of the system therefore will be equal to g into bracket m3 minus m1 minus mu m2 all over this m2 plus m1 plus m3. And that is the acceleration of this system. This is mu. Right. So that is that for this. Now, what of condition 2, where it is a smooth surface? Now, if it were a smooth surface you were given, the only difference is this. So you give me the answer in the comment section. The video is already too long, so let's just finish or wrap up here. If it's a smooth surface, this thing is smooth, so friction will not be acting, or friction will be negligible. So here, what we have is only T2 minus T1. So then it means that this part of the equation is exempted. This part of the equation is exempted. So what you have will not have this. So this is what you have, m3 minus m1 over minus m1, then m minus m2. Just give me your answer in the comment section to be sure that you followed this video till the end. Thank you for watching this video till the end. I'm sorry for the break because I had to do some things. Do well to subscribe to the channel. In this channel, we break things down to the simplest possible level of understanding so that you can get it, especially for physics and chemistry and mathematics. So God bless you as you subscribe and share the video with your friends.